Okay, let's look at a problem here that deals with something we call logistic growth. Okay. Um, yeah, I'm going to show you a graph of this in a second. Okay, and I don't want anybody to freak out considering the times that we're in right now. We're approaching, one would hope, the end of the COVID-19 pandemic. But this question does focus on the spread of a contagious virus on a college campus. Now, logistic growth, when you talk about the spread of a virus, a zombie virus, or you even talk about the coronavirus pandemic, if you go and you look at a lot of the models, they're exponential, right? Because one person infects three people, and those three people all infect three people, and one extra, and then those three people all infect three people, and you get this massive growth very quickly. It's not one person to one person to one person to one person. Okay, so that's why these growths are the growth factor. The higher the growth factor, the faster the spread, right? But what happens is eventually, these are dynamic models, and eventually science catches up and there's a vaccine and people are social distancing and quarantining. And so that doesn't necessarily happen. Okay. But if left unchecked, right, you would get a model that models this logistic function, and I went ahead and graphed it and found an appropriate viewing window here. So you see the exponential growth right off the bat, right? But then what happens is that growth starts to table, right? It starts to plateau. And the reason that this happens, all right, not to get too macabre, is but eventually, as you watch how this grows, pretty much everybody gets infected and there's no more people to infect. Okay, so after this would be after 22 days, okay, almost the entire population would have it. In fact, we get to we could solve for this, but after about almost 31 days, there you go. Right around 31 days is when the entire population has the virus. And there's no more people to infect. There was only 5,000 people to start with. So you're not going to see more than that, right? So that's why we see this plateau happening. This is more of a model of population density than unbridled, unbordered exponential growth that just unkept, that just goes on forever and ever and ever, right? So again, this isn't going to happen to planet Earth. Not every single person is going to get the coronavirus, but left unchecked and without the dynamic model and without advancements in science or any sort of precautionary measures at all, possibly. Anyway, not to get too far off topic. But this says a college campus of 5,000 students, that's where we get this number. One student returns from vacation with a contagious flu virus. The spread of the virus is modeled by this logistic model. And the logistic model is a model that includes exponential growth, but that exponential term is in the denominator. Okay. And it says, Y is the total number of affected after T days, right? How many students are infected after 5 days? I could plug a 5 in here and punch that in, okay, and we'd be done with this one. I'm going to focus more on part B, where it says, after how many days will the college cancel classes? I skipped this part the first time around. The college will cancel classes when 40% or more of the students are infected. So when 40%, okay, of the 5,000 students are infected, 40% of 5,000 is 2,000. So when this number of infected students is 2,000, the college will cancel classes. So that would be an equation that we can solve, right? This is, even though it's a logistic model, this is an exponential equation, right? It has a variable in the exponential level. That exponent's down here, okay, but I can still solve for that. Now, in terms of solving this problem, we're going to use a little math magic here, a little bit of a shortcut. So let's go off to the side. All right, we've mentioned this before. If you've seen it on any of my videos, I call it the switcheroo. This is what I call it in class. It might have a much fancier name, okay? But anytime you're solving for a variable that is completely contained within the denominator of a fraction, okay, which is what we have here, right? T is the only variable and it's in the denominator. If I wanted to solve for this value, what's the shortcut to do so? How do I get it out of there? Well, let's take a much simpler approach and look at a problem like this. If I wanted to solve for x, I could multiply by x, and then I would clear it out of this fraction, right? So then my equation would say 3x equals 2. Then to solve for x, I would divide by 3. So I'd end up with the statement that was x equals 2/3, okay? But if we go back to the very beginning of this problem, the very beginning of this problem started as 3 equals 2 over x. And my final solution was x equals 2 over 3. So that's why I call this the switcheroo. Okay, I should trademark that, switcheroo, TM. Okay, because if you want to solve for a variable that is completely contained within the denominator, switch it with the other side of the equation. When this isn't a fraction, we can just swap these out. Okay, and in this case, that would mean taking this entire denominator and switching it out with this number that's over here. Okay, so my new equation is this entire denominator, 1 plus 49.99 e to the negative 0.8t, and that's equal to 5,000 over 2,000. Okay, so we clean this up a little bit. We have 4,999 e to the negative 0.8t, and this is equal to 5 halves, right? Or 2.5, call it whatever you want. Now, how do we solve exponential equations? We solve exponential equations by isolating the power, right? By getting the power by itself. This is the power. How do we get this by itself? We've got to get rid of our floating constant. So we're going to subtract 1 from both sides, right? I'm going to do this if that's okay, just to keep my hand from cramping. So I'd subtract 1 from here and subtract 1 from here. So we'd have 3 halves. Is that okay? Because 1 is 2 over 2. 5 over 2 minus 2 over 2 is 3 over 2. And then I'd be dividing this by that 449.99. Now you're really not going to like me because I'm going to write this as 3 over, what is that, 9,998. Okay, another little fraction trick. What do you do when you're dividing a fraction by a whole number? That's really 1/2 divided by 4 over 1, which is really 1/2 times 1 over 4, which is 1 over 8. So when you take a fraction and you divide by a whole number, you just multiply. So I took this, multiplied it times the top. You still with me? Now, how do I solve for t? I got to get this variable out of the exponential level. To remove a variable and to bring it down into the base level of this problem, we have to take the natural log of both sides. So we're going to take the natural log of this and the natural log of this, and we get negative 0.8t times the natural log of e equal to the natural log of 3 over 9,998. The natural log of e is 1, and 1 times this term is just that term. And we divide by this negative 0.8, and we divide this by negative 0.8 to get our final value here. Okay? Let's go back to Desmos one last time. Let's figure out what this is. So we had the natural log of 3 over 998 divided by negative 0.8, 1.3. Let's see. Is that about right? When do we get to 2,000? Look at that. Oh, right there. So at 10.14, it's just past 2,000. So I think we're probably right. So we get 10, approximately in the middle of or on the early parts of the 10th day, should we say? Let's say 10 days. Okay, so a little fraction magic, and then solving for the power here. Okay, once we get to here, we're just once we get to here, we're solving for that exponential term. We just had to do the switcheroo to start. Okay, and then isolate the power, take the log, get our answer.